Squirrel cage induction motors. In this presentation, we're going to look at the parts that make up a SCIM motor, some basic installation notes, the different types of squirrel cage induction motors that exist, and finally, we're going to take a detailed look at the information that's present on the nameplate. This is a basic exploded view of a SCIM or squirrel cage induction motor that is three-phase. You'll notice that we have some end bell housings or just items that simply suspend or hold the main rotating item in the center of this huge housing, which is called the stator. The item that rotates within the center of the motor is called the rotor. And this type of motor gets its name from the construction of the rotor that resembles what everyone has had as a young child, which is a pet squirrel. And a pet squirrel inside a cylindrical cage that is retrofitted with bars. Now, all joking aside, it is a weird item for them to have identified the name from, but that is how history goes. The rotor bars are electrically conductive and they connect to these end rings that are also made of the same metal material. So really it's one large metal cage that's electrically conductive throughout its entire length. And often you will also see a skewed sort of misalignment, it would seem, of the bars, as if someone has grasped both ends or both rings and twisted slightly. Now, to increase the torque that this cylindrical item is going to exert when electromagnetic flux is applied to it, we add laminations of iron core in much the same way that a transformer would be assembled. This allows for a reduction of losses and an increased concentration of the electromagnetic lines of flux. The end resulting item looks like this, where the bars look as though they are embedded into the surface of the laminated iron core. The stator is what produces the electromagnetic flux in order to turn the rotor. The rotor bars here and the squirrel cage, which is not shown, sits in the middle of the stator with a very small air gap or very small tolerance permitted between the stator and the rotor. It looks like this if we were to cut it apart. And what you'll notice from this picture is that there are no electrical connections made to the rotating item in the middle, the rotor. There are no brushes, there's no connections, there's no electrical wires that connect to this item here. It is simply suspended by two separate bearings, one at the front, one at the back, and it turns by twisting it with a hand if it's not energized. The stator is enclosed in the main housing of the frame. So this is the frame, and often it has these funny fins on it. These might be a bit exaggerated, and this is to reduce or ensure that the heat can be dissipated readily from the motor. Heat is a motor's worst enemy. The stator is made up of the same type of laminations that we saw on the rotor and that we are accustomed to seeing in transformers. Instead of having bars that fit inside these these tiny little laminated plates, we have windings of motor wire. And motor wire looks much different than the standard type of wire that we use in most of our electrical installations. You'll notice here that the wire has been formed into a specific series of loops. The number of loops is important. The orientation of the loop is important in the stator. The direction of the wrap is important. And all of this is taken into consideration when the motor is designed. Now, this motor winding wire appears bare, but it's not. This is a type of wire that has a thin, clear, insulated coating over top of it that's invisible to the naked eye. You can see here in this picture, there's actually been some damage to this particular wire, probably from an overheating condition. The finished assembly looks like this, and the rotor fits or nestles right in this area, so there's barely enough room for a sheet of paper to go between the rotor and the stator's core. All of this is then dipped into a resin mixture that solidifies everything so that there is no movement due to magnetic flux or mechanical vibration. Because if these windings get damaged, the motor is effectively dead. Now, electric motors are regularly rewound when they reach the end of their service life, and this is a far cheaper alternative when compared to a new replacement motor when the motor is the size of a room. Now, Motor Rewind Technician is a red seal trade in Canada, and this is something that you can transition into if that is something that interests you on the larger size of equipment. Now, three-phase skim motors can be wound from the manufacturer as either Y or delta. Now, this particular image that I'm showing here, it's not important that you memorize or even sketch it. Rather, I want you to see that there is a series of loops, which are the windings in the stator, and they're connected in such a way for this particular motor in a Y formation. Each of these little winding groups are then brazed together at the manufacturer, and the motor connection leads are routed to the connection box, which has all sorts of clever names in the field. That's what these wires are that we see on the side. Now, three-phase motors can be designed as 3-lead, 6-lead, 9-lead, which is very common, and 12-lead, which is what we have pictured here. They're all three-phase, and there's different reasons for having different numbers of leads, which we will look at in a later presentation. Now, to ensure that the leads are readily identifiable, all manufacturers identify them uniquely in the same way. They're labeled as T terminals, and they're T1 through to T12, depending on how many leads the motor has. A 3-lead motor would be labeled T1, T2, T3. A 12-lead motor would be T1 to T12. Now, the circuit conductor and the motor lead are secured together inside the motor terminal box in a pigtail type of splice. And if it's a very large motor, then we use a compression connection with eyelets and a bolt, and we torque them together, and then we coat the whole thing in insulating tape and then electrical tape. Or you can use morettes. Sometimes people prefer on the smaller motors to use a set screw type of moret. And other times there's other brands of proprietary equipment that will allow us to make this connection easily and quickly. Most often what you will see is morettes for smaller horsepower motors that are then wrapped with electrical tape just to ensure that they don't fall off due to the vibration within the motor. There's lots of different types of constructions when it comes to skim motors. We have open frame, and obviously the one on the left here is not a true three-phase motor, but the term open frame is a relevant type of motor construction, usually utilized within manufactured equipment, not something an electrician would install. We have standard drip-proof motors, which are only intended to withstand condensation or dripping of liquids. We have totally enclosed motors, which are, I would say, one of the more common applications, especially in the industrial sector. And then we have hazardous location motors, which are a step above a totally enclosed. And these would be utilized in areas where we are exposing the equipment to an explosive gas atmosphere. We also have some very unique motors that are for specific types of applications. This one is a submersible motor, and it's meant to fit inside the diameter of a deep water well. They're also used in oil and gas. So this type of motor is actually suspended by the pipe that the pump will push the fluid up, and the wires for its connection are zip tied to the pipe. And it could be down a deep well upwards of 100 meters. We have hermetically sealed motor compressors, which are a unique type of motor that is mechanically and permanently connected to the compressor that is used to compress the refrigerant in the HVAC system. The motor and compressor assembly are then sealed inside a capsule and welded shut, so there's no real maintainable items in it. If something goes wrong, the entire object is then removed and replaced in the system. This is what the motor looks like inside the capsule. Motor nameplates come in many different varieties, and we're going to take a little bit of time to really meticulously go through all of the different markings on this motor nameplate so that we have a general idea as to what each item is utilized for. So let's start off with the horsepower. The horsepower of this motor is 7.5. Now, the horsepower represents the maximum mechanical load the motor is designed to turn. It can also be used to calculate the torque of the motor, and we'll look at those calculations in a later presentation. The frame of the motor. The frame on this motor is D132S. The frame of the motor is really in relation to the motor mounting flange, the length of the shaft, the diameter shaft, length of housing, center, height to center of shaft is all determined by this number. And some installations really do require a very precise dimension for the motor installed. Others can accommodate any motor that is readily available. So of course, this is going to be something that is looked up through the manufacturer to ensure that you have the right motor for the application. Case in point are these two motor installations that we have. On the left is a direct coupled system, which requires a very precise motor dimension and an extremely accurate and time-consuming shaft alignment procedure. The motor installation on the right is very common for HVAC and air ventilation systems. It can be easily adjusted for many different shapes and sizes and brands of electric motor because it's on a belt-driven system with pulleys. If I have a larger or a smaller motor, all that I need to do is slide the motor towards the housing or further away from the housing, and there are then bolts to secure it down. I can use different sizes of pulleys to adjust the speed, and I can also get different sizes of drive belts. Service factor. The service factor for this motor is 1.15. The service factor, well, depending on the installation, a motor may periodically experience times when the mechanical load it is turning exceeds the motor's nameplate rating. Now, how much load above the motor's nameplate rating the motor is able to handle continuously is represented by the service factor decimal number. Now, this service factor decimal number is used when determining the maximum overload size for the motor starter, and we find information for that in section 28 of the Canadian Electrical Code. The overload, of course, on a magnetic starter would be the assembly that mounts to the load side of the contactor, which is right here, that's contactor, and the overload is down below. And we would set the dial to the maximum calculated overload permitted, and that would be based largely on the service factor. Duty rating. This motor has a duty rating that is 40C AMB continuous, or CONT. Now, the duty rating is an abbreviation or code describing the degree of regularity of mechanical load the motor can turn. In other words, how often is it being started and stopped? This particular motor says it is rated for CONT, and what that CONT abbreviation is in reference to is the word continuous. What it's rated for is continuous running operation. And this is the least taxing of all the different duty ratings that are available for motors. It means it's being turned on and it pretty much just runs for most of the day. A motor that's started and stopped continually will actually be exposed to significantly higher degrees of heat than a motor that simply runs. Now, in North America, duty ratings are in a word form: continuous, short time, intermittent, periodic, varying, and they will sometimes have a time also associated with them, but that wording will be on the nameplate. In European spec motors, the duty ratings are an alphanumeric code that we would then look up through the manufacturer. You do not have to memorize the European or the standard North American duty ratings, but you do need to have an appreciation for what it represents. The duty rating is also used when determining the minimum conductor size for the motor, as per Section 28 of the Canadian Electrical Code. Stator winding insulation class. This motor has a Class F stator winding insulation. The stator insulation class is a letter code representing the maximum temperature the stator winding can withstand before we start to see failure. Higher temperature rated insulation is seen in higher quality motors and contributes to a much longer operational lifespan. These are used when determining the minimum size of supply conductors, as per Section 28 of the Canadian Electrical Code. There are 5 different classifications of stator insulation. You do not have to memorize what the exact temperatures are for each one, but you do need to know that A is the lowest temperature and therefore used in the cheapest motors. B is the most common insulation class for 3-phase motors. And H is the highest temperature insulation rating, and it's used in motors that have, more expensive motors, as well as motors that are intended to be used in very high temperature environments. Rated speed. This motor has an RPM of 1770. The motor shaft RPM is the speed of the motor shaft when it is turning its rated mechanical load. Now, most equipment connected to a motor shaft will have a maximum speed that it can be turned at, or what it's rated for. Case in point is this restaurant ventilation fan that's usually situated above the grill in a commercial or restaurant kitchen. The motor is in the center. It connects to a large ventilation fan wheel, and that sucks the air up and out around the sides of this unit. Now, if we put a motor on here that turns too fast or turns too slow, we will have problems. If the equipment RPM is exceeded, so I put a motor on that turns too fast, the equipment could be damaged, or the motor could be continually overloaded. Because as I continue to increase the speed of the fan, the wind resistance will also increase. If the equipment RPM is not met, the equipment may exhibit substantial substandard operation, as in the suction capacity of the system might be ridiculously low and therefore not be of use within the restaurant environment. Required frequency. This motor has a 60 hertz system requirement. The motor frequency is the required input AC hertz for the motor to operate correctly. Some motors are able to function normally on both 50 or 60, others are not. And depending on where in the world the motor is coming from, it may have different ratings. And if they make a motor that is going to operate for both 50 and 60 hertz, it means that it can be sold to more individuals. Hertz is a factor that affects the RPM of the motor. Voltage rating. On this motor, we have a voltage rating of 208 to 230 volts / 460. The voltage rating is the required supply voltage for the motor to operate normally. Many motors are able to run on multiple voltages. It's very common to see a high and low voltage option. Many motors will also include a basic wiring diagram on the nameplate to indicate the required connections. And different supply voltages will cause different values of current to be drawn by the motor. This particular motor with the 208-230 means it can operate in the low voltage connection on voltages anywhere from 208 to 230 volts without having any difference of connection. 460 is the high voltage rating, and this would require a high voltage connection inside the motor terminal box with the T leads. Full load amps, or FLA. This one is 21 to 18.8 / 9.4 amps. The full load amps is the current drawn by the motor when rated voltage is applied and rated mechanical load is being turned. The FLA of the motor will differ based on the voltage of supply that has been chosen. And so you can see if we chose to connect this motor to a 208 volt 3-phase source, if it's driving its rated load, it'll draw approximately 21 amps. If instead we connect it to 230, it'll draw 18.8 amps. And if we connected it for the 460 volt range, we would draw 9.4 amps. This is what the connection could look like within the terminal box, although often this is more of a European type of motor where the terminals are insulated and provided a secure backing in the terminal box itself. More often we have motors like this, which we've seen a few pictures of already, which have the individual motors identified T1 through to T12, and we make our connections on the terminal box. NEMA KVA code. The KVA code for this motor is J. The letter code that is used to calculate the minimum KVA the motor requires when starting. It's also used to accurately calculate the inrush current drawn by the motor when first started. Now, the way that we utilize this information is we take the code, the letter code, to a NEMA table. Now, a NEMA table is a table provided by manufacturers. It's not located in the code book, and it is not a table that you would have to memorize. Instead, if given the table, we need to know what to do with it. If I want to know the KVA required to start the motor, I take the code multiplier, so J in this case, gives me a range 7.1 to 8, and I multiply it by the motor's horsepower. So typically, people will utilize the upper end. And this is by no means a standard rule, but for our purposes, we always choose the upper end of the range provided. Now, if we wanted to calculate the motor inrush current, because when a motor starts, it will draw more current than what the nameplate states, we can use this quick calculation in order to validate it. Remember, if it's three-phase, you got to have that three-phase root 3 in there as well. Now, why would the KVA be important? Well, let's take a 10 horse 208 volt three-phase motor with an FLA of 30.8 and a KVA code N. It's 208 volt, but it's going to be supplied through a transformer from a 600 volt three-phase system. If I were to size the transformer, I know I can do the calculation on either the primary or the secondary. If I were to calculate it, 208 times 30.8 times root 3, it would give me 11.09 kVA. But remember, that FLA that we have listed on the nameplate is only the current that the motor will draw when driving its rated load. What this will result in is a severely undersized transformer. The transformer will not have enough capacity to allow the motor to start because the motor will have a significant inrush of current when it is first turned on. Instead, what we do is we look at the NEMA KVA code. For N, that's 11.2 to 12.5. I take the horsepower and multiply it by the code provided, which gives me the minimum KVA that I would require in order to supply this motor for its starting as well as its running. And you can see it's a substantial difference in size. The minimum size transformer is 125 kVA. NEMA rotor design. This motor has a design A. The NEMA rotor design code is a letter code that indicates the standard design of the motor's rotor. This generally also provides some insight or indicates the torque characteristics that the motor will exhibit. Now there's 4 different NEMA classifications or designs. And what we're referring to here is how the bars have been shaped and what the iron core laminations look like if we were to remove one. Now, each one is shaped a little bit different, and because it's shaped different, it's going to have different characteristics when it comes to how much starting torque the motor is going to have and how much running torque. You don't have to memorize the shapes of these, but we will look at them in more depth in a later presentation. And finally, enclosure type. This one has 2 ratings that refer both to the enclosure type. The first one is IP55, the second one is TEFC. The first one we're going to look at is the TEFC. This is a NEMA letter acronym for the type of enclosure. We can find a number of these listed in the Canadian Electrical Code, Rule 2404. It tells us here that the different standard types of motors that we can have for enclosures are drip-proof, weatherproof, totally enclosed, and for this particular motor, the TEFC indicates fan-cooled. The other type of enclosure rating that we can have that is almost parallel to the NEMA letter acronym is the more European side of things, which is a numeric ingress protection rating. Now, we can find information on this in the CEC in Appendix B, 18102, Subrule 5. It's Table B, 18.5. Now, what this provides us with is a very standard numeric rating system. The first number indicates the protection against contact and solid objects. The second number indicates the protection that the equipment has against liquids. We see that this particular motor has a 5.5, which means it's dust protected and low pressure water jets.